Welcome back, everyone, to another insightful video. Today, we're diving deep into selected topics from the first module of the CAPE Computer Science syllabus, with a special focus on computer architecture. We'll start by tackling a question that requires us to first construct a Boolean function from a given truth table, and then to create a combinational circuit based on that function. Let's begin by understanding what a truth table represents. It lists all possible input combinations for a logic circuit and their corresponding outputs. This foundation will guide us as we address the first task, constructing the Boolean function. Essentially, this involves identifying the sequence of Boolean operations applied to the inputs to produce the table's outputs, rather than experimenting with various logic gates, which can be both cumbersome and prone to error. We'll approach this differently. Consider a theoretical scenario where the output column of our truth table is represented by a light bulb labeled Y, which, like any bulb, can be either on or off. Imagine this bulb is connected to a battery by long wires, turning on when the circuit is complete. Along these wires, there are switches, some of which are faulty, allowing current to pass even when they appear off. Our objective is to discern and document the specific switch configurations that result in the bulb being lit. We'll focus only on the configurations that activate the bulb, noting the common patterns among them. There are three such configurations: one where only switch A is on, another where both A and C are on, and a third where A, B, and C are all on. Given that the bulb lights up in each scenario, we deduce that all switches must be operational in these instances, despite any indications to the contrary. Analyzing these configurations, we start with the first, where only A is operational, implying B and C might be faulty since they're off. I'll record this by listing each switch and marking those we suspect are faulty with a wiggly line. For the first configuration, we note down A and then B and C with wiggly lines. This forms our initial configuration. Incorporating the second configuration adds C without a wiggly line, suggesting it works in this instance. Thus, we have A and a wiggly line B plus C. Finally, adding the third configuration of A, B, C without any wiggly lines gives us the complete Boolean function. To formalize this, we replace the word and with a dot symbol in our notation, resulting in the final Boolean function. Writing this in terms of y, we get y equals a dot squiggly b dot, squiggly c plus a dot squiggly b dot c plus a dot b dot c. Having solved the first challenge, you can follow up with my video on converting Boolean functions into combinational circuits to tackle the second part of this question.